Good morning to one and all. Welcome to this session. In this session, we are going to discuss linearity property of Laplace transforms. In our previous session, we have discussed Laplace transforms of elementary functions with their proofs and some examples based on Laplace transforms of elementary functions. In this session, our focus is on linearity property and some examples. Let us see some examples. Linearity property. First of all, let us see what is linearity property. If a, b, c be any constants and f, g, h are any functions of t, that means here we have considered three functions f, g and h, and a, b, c are any constants, then Laplace transform of a into f of t plus b into g of t minus c into h of t can be written as a into Laplace transform of f of t plus b into Laplace transform of g of t minus c into Laplace transform of h of t. That means here in this curly bracket, if there is a combination of more than one functions, then we can apply Laplace transform on each and every function separately. Now, let us see one example. Find Laplace transform of sin t minus cos t whole square. Before applying Laplace transform, let us expand this bracket sin t minus cos t whole square using a minus b whole square identity. Then we get sin square t minus 2 sin t cos t plus cos square t. Now, here I have written cos square t here after sin square t. Here sin square t plus cos square t minus 2 sin t cos t. Sin square t plus cos square t is an identity, sin square theta plus cos square theta, which is equal to 1. So in the place of sin square t plus cos square t, we can write 1, and 2 sin theta cos theta equal to sin 2 theta. So 2 sin t cos t can be written as sin 2t. Then this gives Laplace transform of 1 minus sin 2t. So here there are two terms, 1 and sin 2t. So we can apply Laplace transform on 1 and a Laplace transform on sin 2t separately. That means by linearity property, this gives Laplace transform of 1 minus Laplace transform of sin 2t. According to definition of elementary function, Laplace transform of elementary function sin at, Laplace transform of sin at equal to a upon s square plus a square. So, when you apply this formula to find Laplace transform of sin 2t, here if you compare sin at with sin 2t, here a equal to 2. So, Laplace transform of sin 2t gives 2 by s square plus 2 square. And Laplace transform of 1 is 1 by s. So, here we get 1 upon s minus 2 by s square plus 2 square. That is 1 by s minus 2 by s square plus 4. This is the Laplace transform of sin t minus cos t whole square. Let us see one more example. Find Laplace transform of e power t plus sin 2t into sin 3t. Here before applying Laplace transform, you have to simplify sin 2t into sin 3t using trigonometric identity. So here trigonometric identity sin a into sin b equal to half of cos a minus b minus cos a plus b. Now here Laplace transform of e power t plus sin 2t into sin 3t can be written as by linearity property Laplace transform of e power t plus Laplace transform of sin 2t sin 3t. So here we can find Laplace transform of e power t first, then you can find Laplace transform of sin 2t into sin 3t. Here this is sum of both the Laplace transforms. Now let us simplify sin 2t into sin 3t first. So here first let us consider greater angle term, that is here I have written sin 3t first into sin 2t, which is equal to 1 by 2 into cos of a means 3t, b means 2t. So here cos of 3t minus 2t minus cos 3t plus 2t. When you simplify this, sin 3t into sin 2t equal to 1 by 2 into cos t minus cos 5t. So in the place of sin 2t into sin 3t, we can write 1 by 2 into cos t minus cos 5t. So Laplace transform of sin 2t into sin 3t equal to Laplace transform of 1 by 2 into cos t minus cos 5t. As 1 by 2 is constant, we can take it outside. So you can write it as 1 by 2 into Laplace transform of cos t minus cos 5t. Again, this bracket contains two terms, cos t and cos 5t. So we can apply Laplace transform to both these terms separately. So this gives 1 by 2 into Laplace transform of cos t minus 1 by 2 into Laplace transform of cos 5t. Now Laplace transform of cos at equal to s upon s square plus a square according to elementary Laplace transforms of elementary functions. So here Laplace transform of cos t gives s by s square plus 1 square. We get Laplace transform of cos t by comparing cos t with cos at. So here a equal to 1. So when you replace a by 1 in general formula, we get Laplace transform of cos t. So Laplace transform of cos t equal to s by s square plus 1. In the same manner, Laplace transform of cos 5t equal to s by s square plus 5 square. So here if we write those Laplace transforms, we get here 1 by 2 into s by s square plus 1 minus 1 by 2 into s by s square plus 5 square, that is 25, which is equal to s by 2 into s square plus 1 minus s by 2 into s square plus 25. Now this is Laplace transform of sin 2t into sin 3t. But here in this question, one more term is there, e power t. So Laplace transform of e power t plus sin 2t into sin 3t equal to Laplace transform of e power t plus Laplace transform of sin 2t into sin 3t. So here Laplace transform of e power t is 1 upon s minus 1 according to formula of Laplace transform of e power at, which is equal to 1 upon s minus a. So when you replace a by 1, you get Laplace transform of e power t. So here this is 1 by s minus 1 plus s by 2 into s square plus 1 minus s by 2 into s square plus 25. Here this one is Laplace transform of e power t plus sin 2t into sin 3t. Let us see one more example. Here this is find Laplace transform of hyperbolic cos t plus hyperbolic sin t whole raised to n. Now here cos ht plus sin ht raised to n equal to cos hnt plus sin hnt according to De Moivre's theorem. Cos hx plus sin hx raised to n gives cos hnx plus sin hnx. If we apply this here, you get cos ht plus sin ht raised to n equal to cos hnt plus sin hnt. Now here cos, you can apply Laplace transform to cos hnt and sin hnt separately. So this gives Laplace transform of cos hnt plus Laplace transform of sin hnt. According to formula of Laplace transform of cos hat equal to s by s square minus a square, we can find Laplace transform of cos nt. In the same manner, using Laplace transform of sin hat formula, we can find Laplace transform of sin nt. So if you apply these two formulae, you get s by s square minus n square plus n by s square minus n square. This is Laplace transform of cos ht plus sin ht raised to n. Let us see one more example. Find Laplace transform of 1 plus 2 into square root of t plus 3 upon square root of t. Before applying Laplace transform, let us apply linearity property. So by linearity property, Laplace transform of this whole bracket can be written as Laplace transform of 1 plus Laplace transform of 2 root t plus Laplace transform of 3 upon square root of t. Now square root means raised to 1 upon 2. So you can write it as 2 root t can be written as 2 into t power 1 by 2. As 2 is constant, you can take it outside. So here second term can be written as 2 into Laplace transform of t power 1 by 2. In the same manner, this third term can be written as 3 into Laplace transform of t power minus 1 by 2, because 1 upon root t, that means 1 by t power 1 by 2. If you write this t power 1 by 2 in numerator, here this power gets minus sign. So 3 into Laplace transform of t power minus 1 by 2. Here Laplace transform of 1 is 1 by s. So I have written Laplace transform of 1 here. Now let us see 1 by s plus 2 into, here to find Laplace transform of t power 1 by 2, you have to use Laplace transform of t power n formula. So in this formula, Laplace transform of t power n equal to n factorial upon s power n plus 1. So according to this formula, Laplace transform of t power 1 by 2 gives 1 by 2 factorial upon s power 1 by 2 plus 1. In the same manner, third term gives 3 into, here minus 1 by 2 is there in the power. So you get minus 1 by 2 factorial upon s power minus 1 by 2 plus 1. Now, first term as it is, no change, 1 by s plus 2 into, here n factorial equal to gamma n plus 1. So we have applied that formula here in both the numerators. Here gamma of 1 by 2 plus 1 upon s power 1 by 2 plus 1 gives 3 by 2 plus 3 into, here gamma minus 1 by 2 plus 1 upon s power 1 by 2. Minus 1 by 2 plus 1 gives plus 1 by 2. Now, here gamma n plus 1 can be written as n gamma n. So here in this numerator, you can write gamma 1 by 2 plus 1 as 1 by 2 gamma 1 by 2 upon s power 3 by 2. So we have applied gamma n plus 1 equal to n gamma n here to this numerator of second term. But here third term, numerator of third term, we have simplified directly. That means minus 1 by 2 plus 1 gives plus 1 by 2. So here directly we have written gamma half. Okay. Now gamma half equal to square root of pi. Gamma 1 by 2 equal to square root of pi. And here 2 into 1 by 2. Here both these numbers will get cancelled. So you get 1 by s plus, here gamma half means square root of pi upon s power 3 by 2 plus 3 into square root of pi upon s power 1 by 2. So this is Laplace transform of 1 plus 2 root t plus 3 upon square root of t. Now, in this session, we have discussed linearity property and some examples on linearity property. In next session, we discuss first shifting property and some examples. Thank you.